This is a presentation I've been working on for a couple of weeks now. I've been delivering it a few times at meetups and other conferences. It's called Fast Data Apps with Alpakka Kafka Connector and Akka Streams. So we're going to talk about two things. We're going to talk about what Alpakka Kafka is and Akka Streams, and we're going to dive into a specific implementation within Alpakka Kafka. Since I have limited time, I chose transactions for transactional workflows with Kafka, so I figured that might be interesting. So my name is Shallon Glover. I'm a principal engineer at Lightbend. I'm a member of the Fast Data Platform team. And Fast Data Platform is a commercial product that Lightbend provides. It's sort of like Cloudera or Hortonworks. It's a distribution of stream processors, as well as support for underlying infrastructure. We started with DCOS and Apache Mesos, but we've recently moved to Kubernetes and OpenShift. And we support Kafka for all of these stream processors as well. And that's what I specialize in on the team. So because of that, I've contributed to the Kafka ecosystem, including Kafka itself. I helped develop the Scala DSL for Kafka Streams. I worked on Alpakka Kafka itself. It used to be called Reactive Kafka. It's been around for maybe 5 years, so you might have heard of it by that name. Streamzy is a really neat project. I encourage people to check out if they want to run Kafka on Kubernetes. It's pretty mature. They just released their first production-ready version. And if you use Kubernetes, you'll definitely find that project interesting. And then the DCOS Commons SDK is a library to help write stateful services to run on DCOS and Apache Mesos. So I was involved in that last year. So Alpakka. Alpakka is an open source initiative to integrate disparate systems together. So it's a container project that it's basically a container project around all these different connectors to various systems. It doesn't have any source code itself. It just has documentation. You might have source code in the future. But it's a very developer-centric set of modules to use to connect these systems together using Akka Streams. And we're going to talk about what Akka Streams is and why you should care about it. But it is very similar to other projects out there used for ETL operations like Apache Camel, Kafka Connect. Unlike Connect, it's not declarative. They're just the modules are libraries you bring in, just like any other library dependency. And it helps people build these reactive integration pipelines using a principle known as backpressure, which is one of the key attributes of Akka Streams. And you can write these apps in Java and Scala. So here's a kind of logo cloud of the different connectors that are available. I put them into groups. There's connectors for cloud services, so AWS S3, SQS, DynamoDB, PubSub for Google Cloud, and data stores, pretty much all the big ones you can think of, like Cassandra, HDFS, Mongo, Solr. And then, of course, messaging. We support implementations, AMQP implementations like RabbitMQ, JMS, and of course, Kafka itself. So the Alpakka Kafka connector is the connector to connect Kafka to Akka Streams. And it was formerly known as Akka Streams Kafka, and before that, Reactive Kafka. It actually predates the Alpakka initiative, which started a couple of years ago. It was created by a company called Software Mill about 5 years ago, I think, and eventually brought in as an official Akka project. So I work for Lightbend, which stewards the Akka project. So they brought it into the under the Akka GitHub organization, and as a result, a lot of the Akka committers made it a lot better. It's used by a lot of our clients, our commercial clients, but it's probably one of the most popular, if not the most popular, client library for people who are in the Scala ecosystem, developing Scala apps to connect to Kafka. And it's used in some of our other open source projects too. So Lagom is a microservice framework. It's used as one of the options for message passing between microservices. And it's used in a new commercial product we're shipping early next year called Fast Data Pipelines as the basically the glue between the components in your pipelines. Because it's been around for so long, it's the top downloaded module for Alpakka Kafka. These are just stats for August 2018. I don't have updated ones, but so Akka Streams. Let's talk about what makes Akka Streams unique. So it's a toolkit to provide low latency, complex event processing, streaming semantics using something called the Reactive Streams specification. And it's implemented internally using Akka actors. So like the old actor systems you might have heard of, Akka is a JVM-based implementation of allowing you to build actor systems. It was originally created to simplify streaming semantics within actor systems. So if you're familiar with those, you'll know that there are the most basic parts of them are Akka actors, and then they communicate with one another asynchronously by passing messages back and forth. So that's a pretty low-level communication model, and you can do any kind of streaming semantics you want with that, but it's fairly difficult to model more kind of high-level abstract semantics. So Akka Streams was the reason it was created was to make those streaming semantics easier in various parts of Akka for the types of systems that you're building. So it reduces a lot of boilerplate and makes it easier to build these types of systems with less experience. It's built in an Akka actor system itself, but that's not exposed to the end user. End user can pick up this library, bring it into any JVM project, Java project, and start using it. They don't have to know what Akka actors are. But we'll talk a bit more about Akka actors and how Akka Streams is designed in the next slide here. So the most basic Akka Stream is a source and a sink. A source has at least one outlet. A sink has at least one inlet. And then you have this arbitrary number of flows in between that's doing some sort of processing on your data. And the big difference between Akka Streams and other stream processors like Spark or Flink or Kafka Streams is that they support this backpressure protocol here. And so there's two communication channels. There's two flows happening within an Akka Stream. There's obviously the user-defined messages are flowing downstream, but there's also an upstream channel that's used for this backpressure protocol. And we'll explore a bit more about why you want backpressure, but in a nutshell, it's basically to accommodate the fast producer, slow consumer problem, where you don't want a fast producer overwhelming any of your systems downstream. So this allows you to signal upstream, hey, can you please slow down so you don't overwhelm me and make me crash, because if, a lot of systems don't have well, whatever the weakest point in your system, your internal infrastructure might be, is probably the first one to fail, and oftentimes there might not be a backup, and you'll get some cascading failure across your infrastructure. So backpressure is really good to is a really good way to handle scale like that if it works for your requirements. So the Reactive Streams specification is an initiative to provide asynchronous stream processing with non-blocking backpressure. So Akka Streams is basically an implementation of this. It borrows a lot of the same principles from the Reactive Manifesto, which is a set of principles to build to help build flexible, loosely coupled, scalable systems that communicate with asynchronous messaging. So this spec was spearheaded by Lightbend, but it has a lot of contributions from big companies in the streaming space like Netflix and Red Hat and Pivotal and others as well. So like I said, Akka Streams is one implementation. There's several JVM implementations out there. These are just a few. There's implementations on other language runtimes too. It's not specific to the JVM. And it was also proposed to be included in the JDK, and it was accepted not too long ago. So as of JDK 9, there's a set of types under this package that is semantically equivalent, one-to-one semantically equivalent with with all of the terms defined in the reactive spec. So what we're going to see is over time, once the community moves past Java 8, we'll probably see most people picking up JDK 11. Once most of the community has moved there, a lot of these libraries are going to start having releases that use this implementation instead of their own internal implementations. So this is a little demo on how backpressure works. So each source, flow, or sink here is represented by an actor behind the scenes. And there's several important traits of an actor. One is that each actor has this little mailbox. And this mailbox is basically where the messages kind of buffer before they actually enter an actor to be processed. Each one of these components, they're called graph stages. I'll start using that term from now on. Each one of these graph stages, like an actor, only processes one message at a time. And that's what makes it easy in actor systems to model concurrency. You don't have to worry about another thread closing over the same state that your path of execution might be currently on. Actors give you that isolation, and if you want to model concurrency, you just have more Akka actors, and they all have their own mailboxes, and then they can concurrently do things. But by processing one message at a time, you get a lot of flexibility in defining state. And that's the third thing. Each one of these graph stages can encapsulate state within them. Okay, so to begin the demo, when you start your Akka stream, there's nothing happening, there's no messages flowing until the sink realizes that it has no messages to process, and there's no downstream graph stages. It's the end of the line. So it sends a demand request upstream. So this uses that backpressure channel I showed on an earlier slide. It sends this demand request upstream. It propagates to the flow. The flow doesn't have any messages to give it, so it moves up to the source. And then the source does what the source does and loads messages. In this case, it's loading from a Kafka topic, but you could use another Alpakka connector here and load it from whatever. Once the source has some messages available, it knows that the flow is waiting for messages, so it sends messages to the flow. And then the flow is processing messages, and it satisfies the demand request from the sink and sends messages to it. So the way to get into a little more detail on how this works, you can imagine if, so a lot of people call this kind of process of streaming the pull model, where downstream things are pulling messages upstream, and it can be inherently slow in a naive implementation. So if you can imagine one demand request per message, then obviously with millions of messages, you're going to get a lot of chatter on that communication channel. So the way around that is to request more than one message. So how do we figure out how many messages we can accommodate? So that's where these mailboxes come into play. So in a normal actor system, you have mailboxes, and if you don't specify a different one, it's the default one is unbounded. So it can grow infinitely large, and you can imagine it in certain scenarios that it could grow so large that it would basically run out of memory. So by default, in Akka Streams, the mailboxes for each graph stage are bounded. So it knows exactly how many messages it can buffer, and that's what it sends when it sends this demand request. It says, I can handle exactly this many messages in my mailbox. In practice, you'd probably have a lot more than that. And it sends that along with the demand request upstream, and it's basically the pull side of this dynamic push-pull that we're going over right now. And then the source can then push messages downstream. So it doesn't need to wait for one demand per message. It knows it can send a batch, which is basically what push semantics are doing. They're just batch sending things as fast as possible. And if there's no backpressure, then you can get into trouble with that model. But because it knows it can handle up to 5 messages, that's what it sends. So this is the example of the fast producer, slow consumer problem where, and this is how we handle it in Akka Streams. So once this mailbox is full, there's no more demand requests coming from the flow. So this situation should never happen. The message shouldn't be sent, but if it did, it would be dropped because it can't be accommodated in this mailbox. So Kafka. Show of hands, who kind of knows what Kafka is? Okay, good. I don't have to talk about it much. So there's the quote, big distributed streaming system, fast, high volume, fault tolerant, all those great things. It's a relatively simple architecture, and it offloads a lot of the complexity to clients. So Alpakka Kafka connector is an example of one of those clients modeling some more complex behavior over top of Kafka for interesting message delivery semantics. Kafka is really good at absorbing high load. So it's sort of counter to what Akka Streams is all about. Akka Streams is about accommodating just enough data. You can tune the mailboxes and whatever to accommodate more messages. You can scale them out horizontally and accommodate more load that way. But Kafka doesn't have any means of backpressure. It's designed to accommodate as much load as possible. It's like the shock absorber for your internal infrastructure. You can put it on the periphery, accept like high bursts, spikes of traffic, and then your consumers can catch up at their own speed. But Akka Streams, when it loads data from Kafka, can't propagate backpressure messages over through Kafka unless you modeled that. But I would argue that doesn't make sense because that's not what Kafka's strong suit is anyway. So usually an Alpakka Kafka pipeline, or a pipeline using Akka Streams, is starting with Kafka, and then there are other components that you're communicating with over through different means. So not through Kafka topics, but maybe through just a TCP socket or a gRPC connection. And those means of communicating, we can support backpressure through. So backpressure isn't just exhibited through a single application you have running on one node. It can span multiple network hops as long as those network hops support some means of backpressure. So I already gave a few examples, gRPC and just plain old TCP sockets. So when would you use Alpakka Kafka over Kafka Streams? So they're very similar. They're both just libraries, so unlike Spark or Flink, which are frameworks and require a cluster resource manager in place to do any large workloads. Alpakka Kafka and Kafka Streams are just library dependencies you bring into a JVM app, and then it's up to you to figure out how to deploy that, scale it if you need to. But obviously, backpressure is one unique feature that a lot of these other stream processors don't have. So if that's interesting to you, then this is probably a good technology to consider. Complex event processing. So in most cases, if you want to do any kind of CEP, you're calling out to other systems, which can be a very brittle activity. But with Akka Streams, as you might imagine, it has very good integration with Akka actor systems. And actor systems are a great way to model very complex business requirements. You can have actor systems that are a single JVM. Maybe they're running in the same JVM as the stream itself. Or you can have cluster implementations that span as many nodes as you want. The Akka team once spun up a 3,400 node Akka cluster. I think the cluster formed after about 5 minutes. It's an amazingly powerful way to model complex systems if you have that need. So basically, if you want to do any kind of CEP and you've already modeled, all the rules, all the type of derivative functions you want to happen to this message as it gets processed through a complex CEP loop, then you can easily link to those actor systems using Akka Streams by just using what's called the ask pattern. And I probably won't have time to get into that today, but I encourage you to check it out. And then complex graphs. So Spark, Flink, Kafka Streams, as far as I know, they only support acyclic graphs. Akka Streams actually allows you to implement cycles within your graph if you had that need. Not many people have that need, but it's definitely pretty interesting. If you do have that need, then you can model it very easily without having to basically model it at a higher level through different Kafka topics and things like that. So what I mean by a cycle is just a loop within your pipeline. So instead of just kind of a linear downstream pipeline, you can have maybe a downstream flow sending messages to an upstream flow for whatever reason, to influence that information somehow that's flowing through it. So here's some code, not very interesting. This is just the ceremony to get the clients up and running. So if you've worked with Kafka, this should kind of look familiar. This is Scala code, by the way. And yeah, so you can use type-safe config and have your default client or consumer or producer config in there, and then some other Alpakka Kafka config. You set all the settings this way. And then here's a more interesting example of an actual kind of end-to-end workflow of a very simple Akka stream. And these so this committable source and committable sync here are components of the Alpakka Kafka connector. So this is basically what you're referencing. And you're passing in your connection details, your topic subscription. And this particular source is basically helping you model at least one semantics by including offset information for messages that you're consuming downstream so that they can eventually be committed automatically on your behalf. So you don't have to do it for you. So you don't have to do it yourself, rather. So all your business logic would be in some form of transformations here, like a map and lots of other transformations that are available with Akka Streams. Yeah, and then the like I said, once the acknowledgement comes back that this thing has been committed to or produced to a topic, then it will automatically commit, every single message or a batch, depending on how you want to model those semantics. So normally in this presentation, I jump into consumer groups and talk about managing at least one semantics in more detail, but I didn't have a lot of time, so I chose one particular feature of transactional, of Alpakka Kafka, and that I thought you guys might find interesting. So Apache Kafka supports transactions as of 0.11. That came out June 28th last year. So transactions enable atomic writes to multiple Kafka topics and partitions. All of the messages included in a transaction will successfully be written, or none of them will be. So that should sound pretty familiar. It's very similar to just any old transaction with a database. These semantics weren't possible before 0.11 because a lot of features had to be added to the brokers and to the clients to make it work. So before then, these types of semantics weren't possible. You could try and model them on top of Kafka, but there were certain corner cases that weren't supported where you'll always get there is always a possibility that messages could be out of order. I won't get into the details about that, but basically it's related to how retries work within Kafka. So this solves that. So before we get into the guts of transactions, Kafka talks about 3 message delivery semantics they support. So at most once is the most performant one. Basically, we're sending messages, it's fire and forget. A good example is a game client and server where you don't care about every message being delivered, you only care about the latest message. So it's using the UDP protocol, and which has, it doesn't have all this acknowledgement stuff built into it, and using at most once message semantics are basically the same thing modeled with Kafka, where you're just sending it and you're not waiting for acknowledgements before you send the next one. At least once is what most people want to use, and it's basically sending a message, waiting for an acknowledgement. If the acknowledgement doesn't come back, then we retry sending that message. So there's a possibility that we can send that message more than once, and downstream we need to either just accept that fact or handle deduplication in some way. So that can be a pain. And exactly once is the holy grail of kind of message delivery semantics, and I have it in quotes here because exactly once message delivery, if you want to get really technical, is not possible. So how does Kafka claim that they have exactly once? So let me explain that a little more. So there's a famous problem known as the two generals / Byzantine generals problem that says exactly once message delivery is impossible between two parties where failures of communication are possible. So that seems fairly definitive, but what we're actually doing with Kafka isn't violating this rule, because we're doing some other things at a higher level. So in an IT networking class, you might be learning about TCP. You learn about things like at most once with regards to like UDP protocol, and at least once with regards to TCP. And then they might talk about this, how at that low level you can't guarantee that the message is only received once, processed once, sent once, and lives once in the destination. You just can't make that guarantee at a very low level. You need a higher level of abstraction and a more application kind of specific point of view to make that kind of thing a reality. So that's the key, basically. So exactly once message delivery at a low level is impossible, but exactly once processing at a higher level using a bunch of tricks or faking a lot of the things to make exactly once delivery look like is possible. So some of the things we're faking are retries until we get an acknowledgement from the sink. So that's very similar to at least one semantics. So we'll retry if a message isn't, acknowledgement isn't sent back to the client. We have idempotent data sources. So when the message ends up in its destination, we have some sort of way of determining that that message has already been sent. So some kind of deduplication is happening. And the last thing is we can guarantee that messages are not processed more than once through a couple features that I'm gonna show you in a second here. So here's the basic breakdown of transactions within Kafka. So you have 5 things I'm gonna go over here quickly. So the transaction coordinator is basically a sub-process that runs in one of the brokers, and it's communicating with a client, and there's one of these coordinators per transactional workflow. It has an internal Kafka topic known as the transaction log, and this is where all the metadata about the transactions happening, stored. You have control messages, which we'll talk about a bit more in a second, but these are basically caps at the end of the topics that you're producing to signal downstream that, hey, anything before these control messages was successfully processed. You have a transactional ID. So this is similar to a consumer group ID, if you're familiar with consumer group. It basically differentiates this program from another transactional program and also fends off any duplicates of that program that might try and trample over the messages that you're processing. So if you have, for example, 2 programs running with the same ID, Kafka will guarantee that only one of them can actually commit a transaction at a time. So they can't both commit transactions at the same time, because then obviously you'd lose a lot of the guarantees that exactly once is trying to give you. And the way that works is by there's a generation, a version number for every session of a transaction that's appended to the transactional ID. It's just called an epoch number. It's just a increasing number that gets appended. So if another transactional application tries to join, it's going to, they call it fencing off. It's going to fence off the older generation of that program and say, roll back your transaction. A new player has entered the game, and your any data you have in your transaction that's not committed is null and void. And then the new application will resume from the latest committed offsets that were, it'll consume from the last committed offsets. So the 3 features that enable transactions in Kafka are idempotent producers, multiple partition atomic writes, and consumer read isolation level. So idempotent producers are really easy to explain. This is all the transactional semantics on the client, from the client perspective, are built into the Kafka producer API. So you have a client here, it's joined the cluster, it has a producer ID. This is a ID that gets generated by your Kafka cluster for you. And it's kind of like a session identifier. And then you have this sequence number that's 1-to-1 for every partition that you're producing to. So for each partition, you have a sequence number. So you're sending your first message here, you're starting from 0, this producer ID, the broker receives it and persists it into a partition, along with that metadata. And now the broker is expecting the next message, which would have a sequence of 1 for this particular partition. But what if something happens where the broker is trying to acknowledge that this message was persisted and that doesn't go through? The client's going to retry, and it's going to send the exact same information again. But instead of failing, the broker can simply say, oh, that's okay, it's still a successful request that you made, but you can stop worrying about trying to resend that message, I already have it. So it signals that there's a duplicate already. If it sent a sequence number, if there was like a gap in the sequence number, like it tried to send 2 before it received 1, that would be a fatal exception for the transaction. Everything would be rolled back. So this is the idempotent producer. And multiple partition atomic writes are required to make sure that the commit process guarantees that all the information, all the messages that were in the transaction, all the messages that we consumed from our source topic have been read. Make sure all these things happen kind of in one operation. So this is basically it's a two-phase commit. So the first activity that happens when you commit a transaction is that it will update the transaction log with a message saying we're preparing to commit the transaction. And then once that's been acknowledged that is in the transaction log, then we can add these control messages to all the topics we're producing to, and we can also commit that all the messages we consumed have been read, and we do this all at once in an all or nothing operation. If any one of these things fails, then obviously the whole transaction isn't valid anymore, so it needs to be rolled back. Once they all happen successfully, then the transaction is committed and everything is good to go. And finally, the read isolation level is for downstream consumers of your transactional workflow. So we described a simple consume, transform, produce, like consuming from Kafka, producing to Kafka. I forgot to mention that before. It has to be the same Kafka cluster, and it has to be consuming from Kafka and producing back to Kafka to get these guarantees. So assuming that the transaction was successfully committed, then maybe you have another transactional program downstream that's consuming from the partitions you are producing to, right? It looks for, if it has this setting of isolation read committed, then it knows to wait for this control message to show up before it starts consuming messages, because it only wants to consume messages that were part of a successful transaction. So the opposite setting for this, if it's not defined, is read uncommitted, and that's basically the old, standard way of consuming from Kafka, which is basically as fast as possible, depending on some other client consistency guarantees you can tune in client config. But yeah, that's how that works. So transactional workflows are actually very fast, and in the design papers that Kafka created when they implemented some of these semantics, they did a comparison where they picked a good interval to commit transactions, like at a certain level of batching of messages in a transaction. The overhead of a transaction was negligible over time. The performance penalty that you do pay, though, is end-to-end latency within your overall pipeline. So if each one of these is a transactional application, they'll commit based on some sort of interval, whether it's based on time or number of messages. Usually it's time. And say it is time, then the latency you're going to see at the end of this pipeline is going to be an aggregate of all the latency of these transactional commits, because it has to commit a whole batch before the next one can consume them. So this is what you got to watch out for when using this in a longer pipeline. So here's how Alpakka Kafka implements this. It's very similar to the way Kafka Streams does it itself. There's basically a loop happening right here where every 100 milliseconds by default, which is the same as Kafka Streams, it will try to commit all of these messages. So what it does, as messages enter the transactional sink, or this can be modeled as a flow as well, the messages are added to the transaction, produced, and then we have a little bucket here waiting for the acknowledgements for every message we're consuming. And then when it comes time to commit, once this interval elapses, we commit the transaction. And we have to do a couple things in order to make sure that works properly. And I'm going to go through a short workflow here of how that works. So the graph stage, this is an example of the transactional graph stage. It has a transactional status. It has a backpressure status. Is it exhibiting backpressure? Is it not? And it has this commit loop, which is basically signaling when the transaction should be committed. And then it has a transaction with the actual messages and that bucket I mentioned earlier. So this is the transaction in progress. The transaction's already been begun in the last slide. It's open now. It's receiving messages. They're coming into the mailbox. They're being committed to Kafka, and these are some of the outstanding ones we're waiting for responses to. And then this commit loop elapses. And the way that we signal to this transactional graph stage, like when to stop receiving more messages, is by sending another message to ourselves. And this is kind of a neat way of modeling concurrency within one actor, instead of actually closing over some code and mutating state, which creates all those kind of race conditions and hard concurrency problems we're probably familiar with. We simply send an internal message to our mailbox saying, this is the message that will actually start the transaction. Any messages after this transaction will not be after this message will not be part of the transaction. In fact, this message itself, when it's processed by this stage, actually suspends the backpressure. So no more messages can actually enter the mailbox. So at this stage, we're draining the messages. We waited for all the acknowledgements. They come back, and we commit the transaction using that two-phase commit, and then we begin a new transaction. So here's the code. It's very similar to what I showed before. It's just a source, transformation, and commit. So yes, that was very complicated, what I just described, all the transactional implementations, but for the end user, the good news is it's really simple and easy to use. The only difference here really is that we have a transactional ID and we're using different source and sinks. So I don't have time to go into all of this, but this is Alpakka Kafka was just released 1.0 milestone 1 on November 6th, a couple days ago. It has a new team at Lightbend that's kind of rebooted it. It's got a lot of community interest now. There's a lot of new features in it. So I hope that you guys might find it of interest. So Akka is basically a toolkit. It's not a framework. You pick and choose what you want to use and build your own streaming platforms or microservices or whatever you want with it. And Alpakka Kafka is just one component of that. So hopefully I've given you some ideas on what you can build and yeah, thanks. That's it.